Welcome everybody to this training session. We are going to be talking about our data structures today. Essentially, please all phones should be on silent or vibrate the thing so that we don't get any interruptions. Let me do mine as well now, because there's people who are going to come very soon. Okay. Our data structures. This is what we're going to be discussing today. We'll talk about atomic vectors. We'll talk about matrices. We'll talk about data frames, lists, and then we'll have a small code demonstration. These are the main structures that we have in R. These ones are listed here. Before that, we have a small recap. The last time we had this training, we tried to go over a few things. One of these is the file system in R. Does any of you remember, assuming, let's say you're in R and you want to look at the files that you have in your you have in your working directory, what command or what function do we normally use? If you were here in the last training, and all of you were there in the last training, or you watched the video, how do you examine your directory, your folder in R? I hope your R is open. You can try it out too. Does anyone remember? Does anyone remember? There's a function called dir. Dir will list the contents of your. Okay. To list the contents of your folder. dir with open and close parentheses. Then the workspace. We talked about the workspace, or what is called the global environment. The global environment is where your R objects, all the objects you create in R, that is where they will reside. So let's say you want to examine your workspace. What function do we use to examine the workspace? Who remembers the function that we use to examine the workspace? You want to list all the objects you have in your workspace. ls, correct. So when you type ls with the open and close parentheses, it will list all the objects you have in that workspace. And if there's no objects in the workspace, what will it give you?
False.
No, it will return something. It will return character 0. Okay, character 0, because as we will learn today, we will learn about character vectors. That list, or the output that function gives you, is actually a character vector. Okay, but I'll explain more of that as we proceed. Then we talked about packages, and we discussed that all our functions are put together in what we call packages. Then we have the built-in packages, the ones that come with your R installation, like the base package, which contains most of what we have in R. And then we have add-on packages that you install. Okay, so packages that people like you and I have put together. Even yourself, you can, if you know what to do, you can put together your own package. All right. Then we did something about importing data. Okay, if you recall, we tried to import some data from a CSV file into R. Okay, what function do we use to import data from CSV into R? How do we use it? Okay, there's a function called read.csv. When you put into that function the file name or the path to the file, the CSV file, it will read that CSV file and put everything into a data frame. All right. Then we talked about R functions. We just did an overview. And we said that everything that happens in R happens it is done by a function. Everything is done in R. Even to shut down R, you use a function to shut it down. When we say Q, open and close, it will close your R session. So everything that we do in R is done with functions. And somewhere down the line, I'll teach you how to write your own functions. Okay, but what functions are is basically it's just routines, subroutines that have been put together. Because every operation or functionality that is being carried out on any computer, it's actually a sequence of commands that are taking place. So instead of when you know that when there are certain routines that are carried out regularly, commonly, repeatedly, what you do is you put them together into a function so that you don't have to write down the whole routine over and over again. Okay, so that's what functions are. Okay, now into our main topic today, atomic vectors. The atomic vector is the first data structure that we're going to look at today. If you look at this picture, you will see two box-like or two rectangular things here. One is called X and one is called Y. And you see numbers in here. So just imagine that these are memory locations in a computer. So in each of these you have a number. This is 2.6, 3.2, 3.8, 4.4, and 5. And down this one called Y has exactly the same thing. Okay? Now in R, if you want to reproduce this structure in R, we use this code to reproduce exactly the same thing that I've shown in the picture. So you can see that we have a function here called C. This C function is called the concatenate function. Concatenate means to chain things together. That's what it means. It's taken from the Latin, which means to chain things together. So this function will chain whatever you put into it together into one unit, into one structure. So we have these very same numbers: 2.6, 3.2, 3.8, 4.4, and 5. And when we apply this function to it, and then we assign this name to it, X. We have called this object X. And similarly, we did the same thing here and call this object Y. But it's just they have exactly the same content. All right. So when we run X, we see that it has given us the output of whatever we put in. But now they are together. They are one object. Okay. And this is what we call data structures. We have each of those numbers are a data item. They are a datum, as it were, and we put them together into a structure. So they are now connected. They are related to each other now. Okay. And then Y has exactly the same thing. Okay. Notice that this R5 has become 5.0. That is because of what you see later on down, as we talk down the line. Please, if you have any question while I'm talking, you are feel free to interrupt me. Now, these vectors are the building blocks of R. In fact, everything that we do in R, of course, you know that R is a language that is designed purely for data analysis. So everything we do in R is based on these building blocks of vectors. Okay? They are more advanced, complex, complicated data structures, but they are all founded on the basis of vectors. All right? So we have different types of vectors. We have character vectors, integer vectors, double vectors, logical vectors, complex vectors, and raw vectors. Okay? Of these, we're only going to talk about these ones, the 4. These 2 here are not important for us to know now. In fact, you may never use them. Okay? But these 4 you will use all the time if you're using R. So a character vector is simply, if you remember what we discussed in the previous classes, we talked about strings, right? So character vectors are made up of strings, and strings are a combination of characters, if you remember, and characters are they are you know, in the low level representation, characters are codes given to certain data in the computer. Okay, they are codes, they are just codes. We will not go into coding now, but if you want to ask about it later, or if you have any question on that, I can give you a brief explanation, but I don't want to waste time on it. But just know that they are codes. If you recall, or if you know anything about what they do in primary school, I think primary level, you know, teaching, they talk about, is it qualitative reasoning? So you see, they'll map a number to a letter. For instance, they say, right, if A is 1, what will B be? So something like that. Or what if you say 2 is the A? What will, if B follows immediately after A, what will 2 be? 2 will be B, while 3 will be C. So this is the kind of coding that we use. It's encoding that is used to give values to characters. All right, at the lowest level in the computer. Okay, so it's very important for you to understand this. So characters are the one type of vector. Then we have the integer vectors. The integer vectors are whole numbers. Okay, 1, 2, 3, 4, up like that. They are whole numbers. Double. Remember the last time we talked about numeric values. Okay, the double is just, call it a real number, a real number that has decimal places, okay, 1 or more decimal places, and although there's a limit to the level of precision you can get on the computer. Okay, yes, sir. But we'll not go into that detail here. Logical is either true or false. Okay, and then complex is something else. You know, the raw, it has to do with bits and bytes. We'll not go into that. This code here gives us examples of the 4 main atomic vectors we're talking about. Yes, you have a question? Okay. So again, we have our function here, the concatenate function, C. Now we have these strings. Okay, now notice that this is a string. This is a string, okay? This is a string, and they are separated by what? By commas. So these strings, this function will take these individual strings and join them together. Okay, and then similarly we have integers. The way to force a number to be an integer in R is you put an L, and a large L behind it. So when you say 1L, 2L, 3L, 4L, 5L, these are all integers. So this will give you an integer vector. The double, if you just type 1, 2, 3, these are doubles. By default, a number you type, like even if you don't give it the decimal places, it will become a double. And what it means is that the amount of memory that is given to it, to give it that level of precision, that is what defines it as a double. Are you following? because if an integer doesn't need the same amount of memory to be assigned to it for the purpose of precision, unlike a double. Pardon?
That's why the 5 had 0 attached.
Yes, in the other example. The logical vectors true, false, t, f, f. Okay, I put them together like this because in R you can actually abbreviate this. If you just abbreviate capital T, it's an alias for truth, and the capital F is an alias for false. Right?
Sorry, sir, for taking you back. What do you describe them double vector as?
A double is just a number. It's a real number. Okay, so if we have something like 1.000, that is a real number. But this one I just created it this way, just with plain numbers. But under it is a double. So it can have, decimal places. Okay, even though when you're interpreting it, it won't show it like that. It may not show it like that, depending on how you on the set. But if you notice the other one that we did, the one that we did at first, it converted it into decimal place. Even though it's only, this one came only like this with 5. But when it was given out the output, you see it has 5.0. So that's why it is called double. Double means double precision. That's what it means, double precision. Okay, so when you print this char vector, it gives us this is one structure together. So these numbers they show you that they are together from numbering from number 1 to number 6. This one has six elements. So this thing you're seeing here is just the index showing you how many are there. So this is number 6 of this structure here. Are you following? Now this int vector, which we have created here, came out as 1 to the power 6. Okay, see the L didn't show here. Okay, but it is an integer. The double looks exactly the same, right? Okay, but if we were to do some tests to show you that this one is double and the other one is integer, then log vector is true, false. You see that T and F came out full with true and false. Have you seen it? We used T, F, F, but when the output has given you the actual representation, which is true, false, false. A single value is also a vector. So even if you have a single value, it is still a vector in R. So there's nothing like a scalar value. If you know anything in maths about scalars and vectors, in R everything is a vector. All right. So even this single number 999, I call it singleton. Now we this function will test is it a vector or not. You say is vector singleton. It says true. So it's a vector. Okay. Now there are characteristics. Vectors must be of the same type. So you can't mix different types of objects into one vector. Okay? So they must be of the same type. And when they are not of the same type, once you mix them, they will be coerced. They will be forced to be the same type. That's what we mean by coercion, and it is done implicitly. All right. There's an order of precedence which I don't know it offhand, but if you look at this now, you see that this is a string and this is a number. Okay, this is a number and this is a string. So we try mixing them. We say mixed, but when you print out mixed, you see that this number has been converted into a string, even though it is still 2, but it's now 2 as a string, not 2 as a number. So you can't use this 2 now to, for example, to do addition. It will not work because it is now a character. Okay. So it has been coerced. So from this one, you can see that the precedence prefers to convert when you put character and a number together. It will convert it from number to character. So character is preferred in this instance. right? If we mix these two now, this is the numbers and the logical. Mix them, call it mix 2. When you print it out, you see 1 2 1 0. So you say it has preferred to convert the logical vector into a numeric one, a double, actually. Okay, so this one will now become false is 0 and true is now 1. Have you seen it? Okay. Then, and actually, by the way, if you remember, I told you in the one of the other classes we had, I told you that true and false, if you want to convert it into a number, false is always 0, and true is any number. Okay, any number evaluates to true if you try to force it to become logical. So even if it's a negative number, it will still be true. But 0 will always be false. Okay. Now look at these two here. I tried to combine a string that is a character vector with a logical one. You see that it has been forced to become character. So the force now has these quotation marks are what shows that it has now become a character vector. It's no more a logical vector. So you cannot use this one to test, do a Boolean test of true or false. It will not work. It has been converted into a string where you have false in capital letters. It's now a string or a word, as it were. Okay. Any questions so far? Now we can also do what we call explicit coercion, where possible. It's not always possible. It's not always possible, but at times it's possible. So where it's possible, it will just coerce. Now that what we had before, mixed 2, which is now 1 2 1 0. If we want to convert it into a character, we say as character is a function that will coerce it by force, explicitly, and this is because everything now has been converted into a character. Right. So these functions are very useful in R. When you're doing a lot of computations, there are times when you want to switch over to character, you want to force it to become something. So use these functions to do that. We have as numeric, we have as integer, we have as character, as logical. We have all those. They all have them. Okay, all the types have those coercion functions. Okay. Now matrices. We are just skipping through these things. Okay, there are many details which I'm not going to. A lot of them will just come by practice, and by interaction we can now discuss more of them and through exercises. So this is what we call a matrix. Okay, you can see that this is a data structure that has data here and has some what you call additional data, metadata. Okay, so you can see it has rows and columns and all that. So this is what we call a matrix. It's a 2-dimensional structure that has rows and columns. Like vectors, it must have only one type. Okay, and it can be created using an existing vector. There's an attribute that is called dim that really makes all the difference. I will not go into that now, but maybe I can show you practically how it works. Okay, but there's what we call attributes, of all these structures. Okay, is an intermediate thing. It's not for your basic knowledge for now. But the dim, this is dimension. It shows you that it has dimensionality. When you use this function on a matrix, it will give you the dimensions of that matrix. So let me just go back. Look at this. You see that we said that it must have one type. So the matrix is this. This is the matrix from here to here. That's where the actual data are, and they are all. What type is this? Double, right? Yes. So this is a matrix that. So if you check this matrix and say what is type, you take double. This is just the row name, and these are just column names. They're not part of the data itself. All right? Okay. So example here, we have taken that our vector before that we made before, character vector. There's a function called matrix. This function will create an object of class matrix, and it has some arguments. Okay, the arguments are more than this, but I only use these two. N row means number of rows, so we decide how many rows we want. We say 2 rows, and then this argument by row means arrange them by rows. So when you're creating it, it will create this way and then create this way. Do you understand? Row by row. Okay, you can create it this way also, column by column. But if you say by row, true, it will just arrange it like that. So you can see that this is our vector. This is a vector of characters. We said how many rows you want? 2 rows. You see, these are the 2 rows. Okay, and because we said 2 rows, the function has already calculated that because this vector has 6 elements, it just creates 3 columns automatically. Do you understand? So you didn't need to specify the number of columns, but you can if you want to. So this is a vector of characters. So it has given us this matrix called CHR matrix. Okay, and then this function called dim. If you apply it to this matrix, it gives us the dimensions. The first element of this dimension is the number of rows. The other one is the number of columns. Okay, this thing looks very, very basic to you now, I know. Okay, but you see, oftentimes when you are dealing with data, real data, you may have a matrix that has 1,000 columns. You can't start counting it. So this is where this function becomes very, very important. You want to know what is the size of this matrix. Dim will just give you the result. Okay, it may be 10,000 rows. You just write that for you, 10,000 rows. Okay, instead of counting one by one, by hand or by eye. Now we can also create a matrix by putting together vectors. Okay, now I want you to notice something that happened here. Remember, we had these vectors we created in the outset. This char vector, this int vector, this double vector, and log vector. You remember these vectors? Now we want to combine them to form a matrix. This function cbind will create along the columns. You create column-wise joining. Let me just put it that way. So it joined those vectors along columns and created a matrix called my mate or my maths. And when you run my math, you see that.
So did you create it yourself?
Yes, this function did it right now. This code you're seeing is being run, and this is the output. This is the result of the code. You're seeing it live. Okay. So this matrix, my dot math, as you can see, the name of this vector here, the names of the vector have been converted to become column names. Are you seeing that? And then if you look at the content, you see that this is exactly what we had before. You recall. But observe that everything is now character. Do you observe it?
Yeah.
Why is it all character? Because initially this thing was an integer vector, this one was double, but now they all because they all have quotation marks, so they're all character. Why is it so?
Because by the coercion thing.
By coercion. I told you that in a matrix, everything must have one type. In a matrix, everything must have one type. So because they were differently typed, they had to be coerced for them to become a matrix. So everything was coerced into character. So you can see from this that actually character has the highest precedence in the coercion order. It has the highest in the order. So everything was changed into a character. All right. proceed. Data frames. This is another data structure, and if arguably, I think it is the most important data structure, not only in R but in anything statistics. So this is the common table that we know, where a column is a variable, and then the row is an observation or a record. This is the commonest thing that we see when handling data. Okay. As you can see, it also has two dimensions. It has a columnar dimension and a row dimension. Now, sorry about this. This was supposed to be an indentation. It didn't come out well. But here you see, it's a two-dimensional structure. Each column is a variable, and it happens to be a vector. All right, and each column is a variable, and each row is an observation or record. All right. Now, I didn't say this here, but what makes the data frame to be different from a matrix is that the data frame can have different types within the same structure. That is where it differs from the matrix. All right. So a data frame, each column is actually a vector, and it maintains its integrity. It maintains its difference. It maintains its uniqueness. It maintains its type. Okay, it doesn't change in any way. Do you understand me? That's what makes that one different from the matrix. So, if I just step back again, you see that this one is a character, right? Public character, whatever it is. This one is just a number. Okay, so you see that these things are maintained. This one is even a date type. It maintains the date type.
Is there the possibility of converting this data frame into a matrix?
Yes, you can convert this into a matrix, but in doing so, everything will have to be coerced into one type. Okay. All right, and when you're doing computations in R, the maxim there is that always devolve to the simplest possible data structure. Okay, so if you have data that are, let's say, they are all numerical and they have rows and columns, the best thing is for you to convert it into a matrix. Assuming you imported a data frame and you notice that everything there is double or numerical, and you want to carry out some work with it, it's best to just convert it into a matrix and use it like that. Because there's some computations you can do on matrices which you will not be able to do on a data frame. For example, if you're doing some linear algebra, for instance, that has to do with vectors and real vectors, so matrix multiplication, all those kind of things. You can do it in R. You cannot do it on a data frame. It has to be in a matrix. You can do all those things that they call inverse matrix, blah blah blah. I'm not going into those things. Okay. So this function, the dim function, also returns you the number of rows and columns that you have. Okay. And then to create a fresh data frame, you use this function, data.frame. Okay. And this will put together, whatever. If you have two vectors, two or more vectors, to just join them into and form a data frame for you. Or if you have two data frames that are of the same same dimension in terms of the number of rows, you can just join them together like that. Okay, so now this function we have used it now to use, those are our same vectors or from before, and we're now creating a data frame. And if you notice now, you can notice that something is different from the matrix, even though they look exactly the same in terms of the column name. Notice that this one now has these numbers here for the rows are applied to it. Notice that these ones don't have quotation marks again on them. Have you observed it? Okay, So this is different. The printout looks different, but if we will not do testing on it, but there are many differences which, as we proceed in the class, we will understand more how to differentiate them. Now lists, the last one. Lists are one-dimensional, just like vectors are one-dimensional. They go in one dimension, but what makes them unique? Yeah, I said that they are also called vectors. So indeed, in computing, in computer science, when you say vectors, we're actually talking about a chained data structure. It goes in a chain like that, right? Like I know of some languages like C++, they also have what they call vectors. It's just an array, a one-dimensional array of data. Okay. So, but like I said initially, if you notice the name called atomic, when we say atomic, the atomic vector is that vector that is low level, has only one type. The list is a vector that can have any type inside it. So a list is one-dimensional, but you can put in anything data into it. All right. So it's also a very useful. It's a very useful data type that is used for different things. So it can contain any other data type. It can contain any data structure. It can contain a vector. It can contain a matrix. It can contain even a list. So you can have lists of lists, right? So it's very, very, very handy. So you can see this example here. We have this function list will create a list for you. So if we combine these two vectors, I call it my list. If we run my list, you see what happens here. Now look at this. We have this index here is index 1 of the list. Notice that it has double square brackets. This one here is the vector. So the vector, this vector is inside this list. The list has its own index. Index 1, element 1, element 2, element 1 of this list is this very vector here, and these are the elements which we already know. The second one is the double vector. Second element is here, and this is the vector, and these are the elements of that vector. Are you seeing it? Okay. Now if I go further, I call another list. I call it other list. And inside this list, I put in the list we just made now, called my list, and then I put the logical vector, and I put that our data frame. So I just jumbled everything together into one structure. And you can see that the number one index, the number one element of this list, is my list. Now this my list has two elements. So you see 1 1 is this one, 1 2. So number 1 of 1 is this, number 2 of 1 is this one. Number 2 element is this logical vector here, true, false, true, false. And number 3 is this data frame. So you can see that where lists are very useful is when you go into things like modeling. You want to put together different things, different outputs into one thing. Okay? And also when we come to what is called object-oriented programming, OOP, where you want to create your own types. For example, you want to create a type called student. A student has a name, has age, maybe has a gender. So you can put them into an object, and then you can program with those objects. You can create programming and give your code more expression. Do you understand? And give it more, as it were, attributes. Yes, like giving it a life of its own. Make it like you are creating something, that is a clear object. Right? So lists are very useful for that. Now we will do a small live demo. What time is it? Okay, we have a few minutes. So we're going to just, if you go to Slack, you're online, right? Yes, I posted something there on Slack. So you open that file, because I want you to open this. This is the script I have here, okay, for creating a vector. I'm going to run this script in RStudio. Next, after this class, we will start using RStudio. I want to open this in RStudio.
Sorry, sir.
Yep.
The Slack, is it a dev solution Slack or another group?
No, another group.
Another group.
I sent you an invite. You didn't see it. Check your email. I sent you an invite. Okay, so you said you weren't able to access your dev solution.
Yes, I've not been
Up to now.
Yes. No, I've not seen Justin.
Let me send again. Let me send again. Call out your email again. Your private.
Shobekzimo, SHOBECKZIMO @gmail.com.
Let's check it. You'll see something there. And then I will have to resend. I have to I'll share it again. So you see it here, eh? You will see this. When you join, you see this, and then just click on this link, these links to get the files. So I'm going to open the create vector.r file. Is this thing okay for you guys? The theme I'm using. Is it the dark theme? Is it okay? Like actually, you want the light one? You like this one better? Huh? Okay. Let me.
Sorry, sir.
Yeah, go
For
on.
each of the files to download, what are we supposed to do?
Just open the file. Just open the file, save it, save the script. You can copy and paste and save, or you can save it directly from your browser. But make sure that you save it as .r. When saving it, if it's because it may give you like .text or something like that, just change it to .r and save it as .r.
Sorry, sir.
And then,
like now I'm on the browser, I just do Ctrl-X.
Yeah, most of them will work like Ctrl-S, and you need to save somewhere on your computer. You know, I told you guys you should have a folder for this your training. So use that. Pardon? Go to training, the training channel.
It's not saying save as type test document.
That's what I'm saying now. You can save it as text, doesn't matter. But after saving it, change the name, change the file name to .r, change it from .text to .r. Otherwise, you just copy, paste, and then if you have RStudio, you can use it in the RStudio. Okay. So I'm going to run.
Is it compulsory so that it must work? It has to be on our studio.
No, you can use the RGUI. Pardon? There are two of what? There are three. No. I just did that one now because of this guy who just joined. I just repeated it.
Sorry, sir.
For him.
This is what I have. So I'm going to do it this way.
No, if you like, no, it won't save that way. It won't save. Just use all files.
Okay.
Instead, use all files. and save it with .r. You understand?
Excuse, sir.
Yo.
He's asking me for password. Should I put in my Gmail password?
No, the one you have for you have one already now. For Slack.
The one
Then use forgot.
Okay, let me give you.
Okay, but if you can, even if you don't get the script now, it doesn't matter. You can always follow. Now let's watch what I'm doing now. I'm going to run these scripts line by line. This line says we are creating a vector called rack with this text, as it were, this string. It's only one string, and then we run prac. Have you seen that? Are you following, please?
Yes.
So we ran prac, and it just gave us back what we assigned to it. Now, what is the type of this function called type of, which we check the type of the object? It says character. str will check the structure of the object. So this is the structure. This thing you see here now tells you the type and tells you what is in it. That's what this function does. It just gives you a printout of, to know, like when you see an object in your workspace, you want to know what is it. Just type str. You understand? Now we're going to now run again a different string, okay, and we see that what is there now has been replaced with this other one, this other string. Now it's a length. This function length will give you the length of the vector, and length is 1. Okay. So we move on. We create a vector with the concatenate function into thank and you, and then when we run prac, it says thank and you. Okay. What's the length? Length is 2. Right. Now, I didn't tell you about subsetting, so this will look strange to some of you, but next time we'll go into it. I will just run the code in advance, so you can just gain the knowledge in advance. So this square bracket will index the vector at the position we have set. Now this vector has length 2. So at position 1 we have thank. Position 2 we have you. Exclamation mark. Position 3, nothing is there, so we have NA. Okay? What's the length of prac? 2. So notice that, you see, I made a comment here. Notice that position 3 has no element and it doesn't even exist. Okay?
Well, how did it come there, sir?
How did it come there?
The position 3.
No, I just typed in this thing here
To test.
to show that what R will give you is NA, even though nothing is there. Okay, it didn't give you an error or anything like that, just told you NA. Okay? So now, bonus functions. There are 2 common functions that I will use to print this here, to print out, okay? Print prac. It just gives you the same thing as when you run it in the console. In fact, when you run something in the console, you're actually running print. Now cat does a similar thing, but you notice that it's different now.
Yeah, the quotes.
The quotes are not there. It has given it to you as just a proper sentence, as it were. Okay, it just printed. It did some subliminal, manipulations for you. That's what cat does.
But sir, what does that cat mean again?
Well, I don't know what it means, but if you like, for those of us that have used Linux, or if you work on the terminal, cat is a common function you use to print out something, to send some text or to send yes, to send something to output, either to the console or to a file. So you can write this into a file or to the console, just to the screen. So it's more of an output function. Okay. So what this thing you are seeing here is not a vector. It's just an output. Are you getting me? Why this is a vector? Evidenced by this one. This one here shows you that this it gives you the first element is here. Do you understand me? Yes. So let's continue. Now I want to extend the vector. Okay. I won't explain everything on this thing. I said set seed. The comments, we can discuss this one later. You can ask me on the group what all these things are if you're keen. But for now, we're just doing vector stuff. Now we're going to create a random vector. Okay. If I run it, okay, you see some random numbers here. Okay, these are just very random numbers, right? So what's the length? 6. Okay. Now, notice what I'm doing here. It's 6, but I want to add something to the 7th position. Okay. So I assign this to prac at 7th position. So when I run prac again, we see that value has been added to our prac, and the length is now what? 7. Okay. Now let's try something else, something crazy. Now we'll add something on position 9. Let's see. Let's even 8 self. Yes. So let's see how crazy R is. So we add something to position 9, and when we look at it, something has been added to position 9, and the one that was skipped has become what? NA. Position 9 is 6.99 blah blah, and the position 8 is what? NA. Okay, so R has taken care of all those things. It has just done the manipulation for us. Now there's another function that is called append. It adds elements to vectors. So we're going to use append. We want to append this number to this vector and still call it the same name. So we run it. What's the length? It's 10. What is in position 10 is that thing that we added there. Have you seen it? Now what is the structure of prac now? Before it was character, now it's numeric. And this numeric stands for double. Okay, if you see numeric, they are kind of like synonyms. When you say this thing, it means double. So it's a double, and it has given us the length is 1. It is of length 10, and it has given us the first few values, just the first 5 or 6 of them. Are you seeing it? And this dot means it continues. So this function is just to give you an overview of what is there. All right, and also observe that it has done approximations. Instead of 5 is now just 2, just to make it compact, so we can just see what is there. All right, so we say is numeric. This one is crazy. Is numeric? It says true. Is integer? It says false. Is double? It's true. So I say it's double is a synonym with numeric. All right. Now bonus function. Okay. Is there any NA? We have a function called any NA. So you want to know are there missing values in something? So in any NA, it says yes, true. There's NA there. So you want to now say which ones are the NAs? So anyone that is false is not NA. Anyone that is true is NA. So you say at this position here, you say true, it is NA. So this is Notice that what this thing has given us now, this is a logical vector in response to this computation on the numeric vector. Now, which one is NA? You want to ask. You say number 8. So the function which will work on the logical vector to answer which one is true among those ones. Do you get me? Okay. Now exercise 3. Now let us now shrink the vector. So you can shrink it. The length of the vector is 10, right? So, and this is what we have presently. So we say prac short 1. So we just selected 1 to 7 of this prac and call it short 1. We say short 1 is this. What's the length of short 1? 7. And notice notice very importantly that this thing we're doing now, prac remains unchanged. The actual prac has not been changed because we assigned to a new object. We made a new object and assigned it to it. So this one it remains unchanged. So if you come here and check prac, you see it's still the old thing.
Okay.
Are you following now?
Yes, sir.
Then we say now say prac. Another method is that we want to get the same type of vector. Instead of saying 1 to 7, say we want 8 to 10. But by putting minus, we say we want everything except 8 to 10. Are you following?
Is that why the minus is there, sir?
That's why it's there.
Okay.
So prac short 2 is the same thing now as the other one. Length. Now to compare them, are they identical? Identical prac short 1 and prac short 2. It says true. They are identical. Follow? Now finally, this one I think I'll leave it for you to go and do it later. Okay, let me just run it. Watch what I'm doing here now. I said prac. I assign to this prac NA at position 9 and 10. At position 9 and 10, I say I put NA. I make it NA. Then I say, have you seen it? Length of prac is 10. Identical prac and prac short 1. So this prac is of length 10 but has only 7 values. Just like this one too has. Remember we made this one earlier. It has only 7 values, but it says when you not test it identical, it says they're not identical, even though they have the same values. But structurally they're different because this one has extra length and has NAs inside it. The other one doesn't have it. So this is when you're programming. Some of these things. Why I'm showing this is that when you're programming in R, some of these sort of things, if you don't know them, they can trip you up. Okay, now we have this question here. Later, you just study it later. All right. Now let's go to the next one. The next file I think is create matrix. I think this one was a bit more simple. Now we say create a simple matrix math for the lecture. Okay. Now use of matrix function. A matrix of number 1 to 12 with 3 rows and 4 columns. The numbers are to run the columns and not the numbers are to run by the columns. Sorry, this is a space issue. Okay, no, it's spelling issue. Grammar issue. They are to run by columns, not by the rows. Okay, so we wanted to run by columns. So we run it first. Let me clear this place first. Clear this place first. Okay. So we're here. So this function matrix, we said 1 to 12. Now this 1 to 12, by the way, is going to be a vector. You know, I showed you something about the concatenate function. This code will create a vector 1 to 12. Do you follow it? If you put a colon between two numbers, it means from this to that. In the order, in a sequence of that is incrementing by 1. So it's just run from 1 to 12. So that's what we have here, a vector. 1, 2, 3, 4, 5, up to 12. Now we want 3 rows and we want 4 columns. I want it to run. We said by row, we said force, meaning we want it to run by columns. That's what we have created here. If you run it, you see the matrix here. All right. You see, it is 3 rows, it's 4 columns, and it runs by columns: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. Good. Now I want to use cbind. We said here, add a column to the matrix using the numbers 8 to 6. That is backwards. First, make a vector of the right length. So we call it call-vec. We say 8 to 6. So you notice this same notation where we use this operator, the colon. We need to go backwards, 8 to 6. Because of the way we have placed the order. So this will be, if you run callback, see it's 8, 7, 6, right? Now bind it to the matrix. We say cbind that same math, and then we put callback. This should create a new matrix that has. Okay, so this is a matrix. This is the same matrix. Okay, the difference here now being that we have another column here, and of course because this column came with the name, it carried the name over to the matrix and as a column name, because this name here was applied to this name. Okay, so that is done. Now let's use rbind. Rbind does the other side. It binds by rows. Okay, so add a row to the bottom of the matrix using numbers 77 to 81. All right, make a vector of the right length. So we do that from here. Row vec. All this thing I'm doing now, of course, when you have the script, you can run this thing on your own to practice it, and then of course you can even modify the script to test out 1 or 2 things. That's how you learn. Okay, feel free to play around with the script on your own. Now row vec is this 77 up to 81, right? 5, you can see with the naked eye there are 5 elements here. That is here. Watch here. This is where it happens. All right. Now we say rbind. We're going to bind this row to the same matrix. So when we now check it, we now see how these numbers have been added at the bottom, and similarly the row name has been added. Okay. Oh, great. Now let's remove dimension names. Names were added because of the vectors we created, but we don't want them for the exercise. Okay, so now note that we only created vectors first for easy understanding of our beginners. Normally you wouldn't create your vector like this. It's just because I was trying to teach you something. So let's get rid of the names. So we said these dim names stands for the dimension names, both the columns and the rows. Okay, we also have a function called row names and call names. So if you want to target them specifically or find them out specifically, you can use it. But you want to get the 2, say dim names. Okay, so this function should remove those dimensions. So we say, you see how they are now? They've gone. Right? Now, note well. Actually, all of this could be done in fewer lines of code, but it's good to understand the logic this way. So, like I said, all of these things I've done now can be done even in just 2 or 3 lines of code. I'm just doing it lengthwise so it becomes easier for you to understand. Now, your turn. Create a vector with 10 random numbers between 10 and 20. Okay, so set this to 1. So I'm just doing it random numbers. Okay, now create a vector called first name with 10 random first names. Create a vector called first name with 10 random first names from data in the baby names package. Download and install if necessary. Right? Bonus, write a line of code that will enable you to check if a package is installed or not. So this package, I think I already have it. I don't need to install it. Yes, I have it. So I skip that step, installation. No, if you want, like if you're running this code now, if you don't have the baby names, once you run this particular line, install packages, it will install it for you. It's download it and install it for you. Now, if you want to read about the package, see this help package equals then baby names. It will give you it will open a help file about the package that you can read. Okay.
Are we downloading it from GitHub?
No, just from out here. It will do everything for you. You don't need to bother about it.
Okay.
Yes. So this baby name is a very useful package for data, practicing with data and all that. It has US baby names 1880 to 2017. There are thousands of, I think about, no, is it thousands or millions of, how many names? There are plenty of names. I forgot how many there are, but it's a massive data set. Even Nigerian names are here. Yes, because you know there are many Nigerians in the States, so you have all those names. They're all there. So even for Nigerian, I use this package for even Nigerian analysis to check some names because they're also there. All right. So let me just bring this down here. So the baby names, the data sets, the structure. You can just look at this same STR. So it says here. Now this is class table df table data frame. 1,924,665 observations. So there, yeah. So this is a massive data set. It's almost 2 million, and 5 variables: the year, the sex, the name, the number. This N, the number of people that have number of babies that were given that name in that particular year, and then this the proportion, the prop. The details are here in this place. If you look at this, you will see the details of the data set here. Okay. All right. So let's continue. All names. So all baby names. With this code, I'll grab all the names. Now, this code, I want to just get. Remember, you recall what we're trying to do here. We said create a vector with first name of 10 random first names. Okay, just 10 names. So I want to just pick 10 names out of these ones, out of all these millions. So this code will give us 10 names. All right. I'll skip all this. Okay. Because I was trying to this bonus question here. Okay. Now create a vector with a sequence from 1 to 10. Call it serial number or serial no. That's it. This code will do that. But of course, there are other ways of doing it. Now, using the vector from step 2 above as a guide, create a character vector with elements M and F, name, gender. Thereafter, convert it to a categorical variable that is a factor. Bonus: factors levels are presented alphabetically by default. Make it such that when you run levels gender, the first element is M. This will confuse you. Let me just run it. We can discuss all this later. So gender Gender. So this is gender. Now create a matrix called rand mat with columns in this order: serial number, first name, gender, and the one with the random numbers. So that's it. So this is our matrix. Okay. So examine the matrix. What you notice? Let's look at type of. The type of the matrix is what is character. So everything was changed to character. Even these numbers. Have you seen it? That was what I was trying to show here. But like I said, you run this code on your own. On your own. Then when you have some questions, you post it in the group and then we discuss it. Okay, especially this area here. I know that this area may confuse some of you. This number four area. Now next script we'll run, the last one, is create lists. So this is about lists. So note that the function arguments used in this sample script are rather verbose, and just to enhance your understanding, you do not always need to specify arguments. The functions have arguments, and those arguments they have names. When you are running a function, you don't always need to run the name of the arguments. But we will do it here because to enhance your understanding of that. But once you know the function well and know the position, you just need to put in the arguments. What we have is parameters. This is a function run if, and these are the parameters, and these are the arguments you are supplying. Okay. You see this n equals this, min equals this, max equals this. So those are the parameters, and the argument is what you are supplying to it. All right. But even without this n and this min and this max, if I just put in these three numbers separated by commas, the function will still work. That's what I'm saying. Okay. All right. So we create a vector first, numeric vector, and then we say identify negative values of numbec, label them as true. That's what this function here will do. All right. I will not go into the details, but I'm just concerned with the outcome. We can discuss more on this later. So make a character matrix of 4 color names. The colors are yellow, red, fuchsia, and orange. So we call it. We put it into this object, this vector called X, and then we create a matrix with it. Okay, using all these arguments, data, the number of rows, and then by row we say true. Okay, now add a row at the bottom of colored with the elements called blank. So we have this character matrix here, we put R bind, and then we put under it blank. Have you observed something about this code compared to the last one that we used in matrix? The code is a bit more complicated here.
Yeah.
Yes. Okay, it's somehow deliberate. I'm trying to show you, stages. Yes, so the levels of complexity of coding. For example, here you see that we have this parenthesis here that is outside here. What this will do is instead of, you see, when we run this code here, nothing happened. But if you run this code with this para outside here, it will print out immediately. It will create the object and also print it out at the same time. Instead of typing it below again. So it's one of these that you can do in R. So you see that it has given us the matrix here already typed out. Have you seen it? Okay. Now we are here. Collect names of files in this and the immediate 2 parent folders. I hope this will work. Do I have parent folders? Okay, I have. So this I'm creating a list. This list files is the same thing as your dir. Note it, please. It's the same function, just different names. So it will list. I want to list the files in this folder. List the files in the folder above, and list the files in the other folder above, the other parent. That's what these three things, and they will all be inside a list. Because list can contain almost anything that you can think of, and I call it tree with 3 E's. So thank God, no error. Good. So now create a function that displays the area of a circle for a given radius. So I'm now creating a function called circle, and this function has one parameter, r, which is the radius. And if you know your maths, the area of a circle is pi r squared. Pi r squared. So pi. Remember, I showed you in that r has a constant called pi. If you do pi in you went here last time. If you do pi like this, it gives you pi. This is pi, the value of pi. So it's an inbuilt constant inside r. So if you just put pi times pi r squared, this r squared is r times r. I put it into brackets, so it is squared. So these two will multiply first before you multiply this one. So pi r squared will give you the area. So that's what this. So whatever I put here as a number, it will calculate the area of the circle for me. That's what this function will do. Okay. Now collect the definition of the function table. Remember, I told you if you want to see a function definition, just type in the function name and remove the parentheses. So what this thing will look like, let me show you what it will look like. Table. Oops. Table. Now without the parentheses, this is what it shows you, the function definition. Are you seeing it? This is what happens inside that function table. If you run it, this is what the code that runs inside it to give you the output. Okay, just table. Okay, so I'm saying now put this whole thing as an object. So it will be like a vector. Okay, so into this other object, so I call it table underscore def. So that's what I'm doing here. Now download a CSV file. I hope this will work for me. Download a CSV file from the web and use to create a data frame in R. So let me just pray it works. Trying URL. So it has downloaded the thing. This download file will download this, to go to this URL and download it into this file. I call it Microsoft underscore sample.csv. And this mode is just it's called W. This to writing mode, to write the file. Now read the CSV that I've just downloaded into this one called DF. So I run it. So you'll find that I will have a data frame called DF. By the way, how will I check my workspace to know what is there? Remind me. LS. If I do LS, I'll see what is inside my workspace. LS. Oops. So you see all these things that I've been creating, they are all here in the workspace. Okay. So I want to create another one, car to raw. I want to convert this. This is my former place. National, blah 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 blah. Okay, now convert this one into a raw, from character to raw. You remember I was telling you about raw vectors, huh? Yeah. If you run this hex, you see that it's a raw vector. It's going to be just. That's it. These are bytes. So this is the bytes. You remember I was telling you about encoding. The underlying number values for all these characters. These are the bytes for all of these things. Okay, and I call it hex. And I say, okay, I change this. Give me this old stuff. I changed it before. Okay, I call it necessary in bits, raw to bits. So from raw, you can go to bits even. Raw is what you call hex. Those of you that did electronic, you know what this one is now. So if I say, oops, I'm sorry, very sorry. If I run this in here now, if I just run this bits, you now see the actual bits. So this is like the lowest level, the zeros and ones that give us all of this thing here. Okay.
That's from that, from X, we define the chart to raw as X, which gives national environmental standards.
Hex.
Yes.
Yes.
Now, how did you redefine it to be necessary in bits? I don't understand what played out there.
This is a function that will convert a character vector into a raw vector.
Into a raw vector, yeah.
And that raw vector is in the hexadecimal form.
Yes.
Okay. Now I want to convert the hexadecimal form into the bits itself.
Okay.
And the bits are the zeros and ones that make up all the computing that we know of in
Were you the
software.
that defined it as?
No. These are R functions.
Okay.
These are R-based functions. They exist inside R. Yes. Yes, to raw. So this 4E I think stands for the N. This one stands for the A. I think so. Whatever, you understand now.
But the necessary bits, you defined it that way.
I defined it. I created another vector containing only the bits. You understand me?
Yeah.
Okay. Now I will compile all this into a list. Everything I've done here, all these things, non-vec, colored, car mat, tree, circle. These are all different kinds of objects. I call it mumbo jumbo. Okay, I didn't run this circle. Sorry, so it gave me an error now. I didn't run it. I didn't actually run this function. So I didn't actually define it. So now if I run mumbo jumbo again, it should run properly. So everything is now here. If you want to now display mumbo jumbo, it's real mumbo jumbo. You see all kind of this. Everything is here combined. Have you seen it? Everything is inside one object called a list. The list carries everything, carries anything you want. I once used this thing to summarize files in my office one time. They were shocked. I used lists to summarize them. So everything is here. Okay. Now what is the structure of mumbo jumbo? This is it. Okay. So every item is. Let me widen this a bit so it's clearer. You can see everything here. It's a numerical vector, a logical vector, a character vector, character matrix. Because you can see that it has two dimensions. This is another character matrix. A list of 3 is here. A function is there, right? Another function is there. A data frame is there, and then a raw vector, and another raw vector. Have you seen it? So these are. I'm just showing you what a list can do. It can do practically anything. So what type of mumbo jumbo is called a list? Now, to emphasize that you can have lists of lists inside lists. Look at this this function. I got this function from this book. I called it lister. Now we have list 1, list 1, list 1, list 1, all of them nested, but we have only one as a value inside a list that is nested 4 times, maybe 3 times. So if you run lister, this is how it looks. The only value here is 1. Are you seeing the 1 here? Okay. So we have a list of a list of a list of a list, and then the value inside it is 1, and it's a vector of length 1. You see it? Structure of lister. So you can see it here. List of 1, list of 1, list of 1, list of 1, then numerical 1. This is the structure of this thing that we have touched on here. The type of is a list. Okay? So I think with this we end our class for today. Do I have any questions from you? Or did I succeed in confusing you? No, but that's why I did the script now, because you can go home and it's something you have to step through. Step through on your own. You step through it step by step, quietly, and then tinker with it, change some things. You understand me? That's how you will need to understand what's happening there. We have that our chat. If you have any question, just fire me question. Because that's how you learn it really. Hands on.
Is that this place is where you're composing characters to numbers, like coding. I don't even know how to put it.
Where in the slide?
No, you know that hex character to raw.
Over here.
Yes. You know when that national.
Over here. Yes, good.
When you run the program.
Yes.
It was converted to numbers you called bytes, and then later to bits.
Yes.
Now, I want to understand actually what is happening here. You know, in elementary computer science, there's what is called ASCII code.
Yes,
so
ASCII.
A character like A.
Yes.
A number value in the computer.
Yes.
Is this similar thing?
That's it now. This encoding we're using for now is ASCII encoding. We're using ASCII encoding, or maybe UTF-8. Now, for example, if you look at this thing, let's look at this thing closely. It's a hex, right? If we just examine this hex, what is 4E in hex, in hexadecimal? Can you calculate it? 4 times 16.
That's 4 times 15.
No, 4 times 16 first. That's 64 plus what? What is E? E is 15 now. So 64 plus 15 is 79. The ASCII table. Let me open the ASCII table. There's this in here. There's this thing here for ASCII table. What happened? Why now? Okay, this is just decide not to respond now. This browser. Okay, I have there's a site. The site I think I even bookmarked it here. ASCIItables.com. Yeah. So 79 is what? Four E here. See 4E now. 78. 4E is what? N. Okay?
Yes, sir.
So you can see that that's N here, right? Okay. 61. Hex 61. 61 is what? A. Small letter A. Have you seen it? See this table here. You see how you have the decimal, the hex, the oct, then the HTML whatever code, and the actual character. You can see it here. So for the hex 61 is A. So you see that this hex here, all these codes here, one by one, they represent one letter of this, including the space, one character, the letters and the space and everything, all the punctuation. They are all represented in that code, and that's the ASCII code. So this is hex. But what we are doing here in this character is converting, because the hex itself is not the lowest level. The lowest level is the 0 and 1. That's binary, from hex to binary. So what you are doing here now is you're converting from hexadecimal to base 2. So from base 16 to base 2. That's what this function is doing. Do you understand it now?
But I now give you the name as necessary bits to identify it.
Yes. Because if you want to program, you must give your data, give it names. Give it names so you can program with it. And you can give it meaningful names. So that when you're coding, it makes meaning to you. And also someone else who comes to your code will now know, okay, I'm now saying, okay, this is Nesria. Okay? I said Nesria in bits. It makes some meaning. Do you understand? Any other question?
Okay, so there was somewhere I think when you were listing out, towards the end of the list, when you
Yes.
said there's a character, but the character is in matrix format or something. How do I identify, okay, a character that's in matrix form or just simply a character?
Yes. We have one. We have our character matrix, right?
Yes,
We have our character matrix here, don't we? Then we have our character vector, right? Like this. Okay. Now you're asking now, assuming the name wasn't so clear that it's matrix and vector, how would I know that one is because when you say type of, it tells you character. Correct? That's what you mean. If I say type of the other one too, it's a similar output. Type of character vector is also character.
yes.
So you're asking me how can I know whether one is a matrix or one is a vector? Okay, that is it brings us to a topic that I have not yet shown you. A very important topic. It's called class. If I say class of character vector, it tells me character. If I say class of char matrix, it tells me matrix. So that's how you differentiate. Now this class is to do with we have the typing as in the fundamental type. Then we have what we call custom typing. That's where we wouldn't call it kind, but it's still a type. But that brings us to the realm of object-oriented programming. That's where classes now come to play. Okay? So the matrix itself, maybe when we discuss further, maybe even on the group, there are so many things that I can tell you, but not here. That's why we need to interact more, because there are many things that I'll be showing you. There are so many things, so many things about all this. For the matrix, for instance, if you remember, we used a vector to create a matrix. Now, what our actually does is just to append some attributes to it, that vector, to make it to turn it into a matrix. It's still the same data, the same underlying data. Do you get me? So that's what the class is all about. It's a custom typing now. It's no more fundamental type. It's now a custom type, and that's what the matrix is. Okay. Any other question?
The question I will ask is primarily to begin to make inputs into that operators, the place you are typing in your code. Is there anywhere one can see the list of the characters, what to use, how to use that less than, greater than, with hyphen to make inputs?
I don't understand.
You know, the what we have shared now is still, to me, you have to, is still, is there anything for lower?
Yes, because you have joined us already. We have already done classes.
That beginning class.
No problem. We have videos. We have videos of the beginning class. We will in fact, they're even on our channel, so you can go there and view them. Yes. So once you view those videos, even the slides, they are all available. So you just study the initial material, because what you're asking for is like, is there a way you can even find because there's no way to even memorize all these things.
Of course.
So there's
by practice, but
not even that. R has even a system whereby you can even check things, check functions. For example, now if you say matrix, if you want to check about matrix, what is matrix? If you do this question mark matrix, you will just get a help file open for you that tells you about the function. Do you understand now? Okay. So those things are all part of the R system. But we have already treated all these things before. So if you look at those videos, you get your bearing. It's not about 3 or 4 videos. I think 3 or 4 videos. It's not really too much. Yes. Okay. Any other question? Choose. You have answered everything I know. Yeah. Okay. All right. So thank you very much.
Thank you.
Call it a day. Next time we'll talk about we'll talk about the same thing, but I'll go into more detail. So as I do so, we'll rehearse some of these things. But please, like I said, let's use that platform to gain more knowledge. Thank you very much.
Thank you.
Okay. Bye.